Okay, first of all, I would like to thank the organizers for giving me the opportunity to talk about this work in collaboration with Adrián and Romain. It's having an honor to work with you guys. I have to say that. So, today I'm going to try to answer one of the most common questions in every spatial infinity talk. Where are superrotations? We always have the same questions every time what we give a talk on this spatial infinity story on asymptotic symmetries. So in order to do that, I'm going to give you some very brief introduction of BMS symmetries, BMS4 symmetries, in the context of gravity. Then I will try to introduce and I will try to show very briefly the work of Marc and Cédric, Marc Genoa and Cédric Trossard, about the canonical realization of the BMS4 algebra when you approach null infinity. Then I will go directly to the superrotations at the spatial infinity. So in order to do that, well, a lot of job have been done in order to canonically realize the symmetry. In particular, of course, we have to relax the asymptotic conditions. One of the main points of this relaxation, or one of the keys of this relaxation, is that in the same way as in the null infinity analysis, we have to relax the metric at the boundary. So we are going to allow the metric at the boundary to not be fixed at infinity, okay? That's the same that happens when you try to realize the symmetry when you approach null infinity. Of course, because we have relaxed these asymptotic conditions, we'll have to cure some problems. In particular, there is a problem with the symplectic structure. So the symplectic structure actually is divergent, linear divergent, and logarithmic divergent. And well, the way that we cure this problem is by considering some renormalisation procedure. So the same kind of renormalisation that are usually used in the context of null infinity. Then we will follow the canonical approach in order to define some surface generators, so the generators of the symmetry. We will find that the generator is non-integrable. It's nice that we were able to prove that to show that the generator is finite. And actually, the important thing about the modification of the symplectic structure allows us to have a finite generator of the symmetry, but the generator remains non-integrable. So in order to cure that problem, we have introduced some boundary fields, which is somehow, and I will be very precise about how is this related to a boundary graviton at infinity, spatial infinity. We were able to compute the algebra of the generators of the symmetry by using the canonical approach. The algebra closes, of course, and closes with a nonlinear term. I will explain later what is a nonlinear term in our context. And I will finish the talk with some comments and remarks. So let me just start with this. If we want to introduce BMS4, or we want to introduce this infinite dimensional algebra, the best idea is to start with the Minkowski spacetime. Here we have this Penrose diagram. We have actually three different infinities where we can approach the time-like infinity, the null infinity, and the spatial infinity. The first work introduced by Bondi-Metzner-Sachs was related to defining some asymptotic condition when you approach to null infinity. For that, the best coordinates that you can use are the Bondi coordinates, where this is the precise form of the Minkowski spacetime in these coordinates. You can prove, you can show by solving the Einstein equations that this is not the most general, but this is one of the solution space of this four-dimensional asymptotically flat matrix is given by this expression here, where the relevant quantities are the Bondi mass, the angular momentum aspect, and the Bondi news, which are the ones that are encoding the gravitational waves. This is an analysis that you do when you approach null infinity. So now you can ask, what are the symmetries that respect this? So what is the symmetry that? So what is the invariance of these asymptotic conditions? What you expect is to have the symmetries of the Minkowski spacetime, just the Poincaré group, but what Bondi-Metzner-Sachs found in the 60s is that you actually have an infinite dimensional extension of Poincaré, which is called the VMS group. And this is related to the fact that now you have a vector that preserves this asymptotic form, and that is given by an arbitrary functions on the angles, okay, by T. And this was called super translations. Now we know that there is well, most of you are aware about the fact that there is an even bigger extension of the Poincaré symmetry, which is called the superrotations. Here there are at least two cases where this superrotation can be given. One is the case of Virasoro cross Virasoro direct product with the super translation. This was introduced by Varnich and Trossard some time ago. And there is another one which is going to be the relevant in our case. Is the one of the diffeomorphisms of the two-sphere direct product with the super translation. This was introduced by Campiglia Lada and afterwards fully understood, I would say, by Compere, Ferrucci, and Rossiconi. Well, unfortunately, and as I already mentioned at the beginning of my talk, superrotation have been elusive in spatial infinity settings. Now, why is important to think about spatial infinity? So we know that this VMS symmetry do not live invariant the boundary condition at null infinity, but are also symmetries, exact symmetries of the theory, leaving the action invariant up to surface term. So there is no reason, or there is no reason to think that. So they should appear in any description, in particular in slices adapted to null infinity, to spatial infinity. And so now, if you are adapted to spatial infinity, you know that there is a canonical approach that allows you to compute the charges, the conserved charges, using the canonical techniques. And since there is no flux through the spatial infinity, we know that well, it's quite likely that we will have some conserved charges and everything can. So you can use the canonical techniques, meaning the Hamiltonian approach, which is something that I'm going to use here. However, in this analysis by Ergetelkenboim, this very old paper from the 70s, the VMS4 was not found. Okay? The asymptotic symmetry algebra, asymptotic symmetries were found to be just the Poincaré in this paper. So it was not until recently that the Margenot and Cedric Trossard found a way to introduce this VMS symmetry. So on the way that well, I will show precisely how they did this, but in a summary, they have proposed some very twisted boundary conditions. So there is a relaxation on the asymptotic conditions, such that now they are invariant under the full VMS4 algebra, so invariant under super translations. Well, after that result, we have been, well, I'm included, we have been trying to follow some kind of program, trying to understand the asymptotic structure when you approach spatial infinity. And for that, we have done some work on the case of supergravity. So we have canonically realized the super VMS algebra, super VMS for algebra. There is also some work on higher dimensional VMS. So in particular, we canonically realized the VMS5 algebra. And there is also something very interesting. I'm not involved in this work, but you can also consider some logarithmic super translations. And it was shown in a recent paper by Mark and Oscar. I think Cedric is also involved somehow. That this is logarithmic super translation are very useful in order to make sense to this momentum ambiguities of the momentum the ambiguities of these super translations. Okay, but I'm not going to talk about that today. So let me go directly to the theory. So for this, we have to introduce the Hamiltonian action for pure gravity in 4 dimensions. The theory involves some induced metric, the conjugate momentum, the lapse and the shift that induce some Hamiltonian and momentum constraint, respectively. It's important to comment that in this approach, we have to add some a boundary term that is there in order to have a well-defined variational principle. Now, in this work by Regier from the 70s, they proposed this boundary condition, this follows for the metric and the conjugate momentum when you approach spatial infinity. What you can find from this asymptotic condition that there is actually logarithmic divergent in the kinetic term, so in the kinetic term of the action, that can be cured by setting some, by choosing some parity condition on these arbitrary functions, okay? Such that this is odd, so this is actually zero. Unfortunately, as I already mentioned in the work by Regier from the 70s, they were not able to find the super translation symmetry, so the asymptotic symmetry group. So this asymptotic condition were invariant only under Poincaré, not the BMS4 algebra. And now, and this is the important thing about the work of Mark and Cedric, is that they have introduced some relaxation on the asymptotic conditions such that they allow some twist in the leading term of the fall-off of the metric and the conjugate momentum, such that they allow some extra piece that goes precisely as a linearized diffeomorphism. What is important and why is relevant? Because, for instance, this asymptotic condition now accommodate the tap-nat solution, which was not the case before. Of course, since we have relaxed the asymptotic condition with these extra pieces here with a definite parity, all this complicates the charges. So this makes the charges not integrable in principle, and also you can also find some divergences in the symplectic structure in the kinetic term. But what is interesting what is important to have precisely this structure is that this allows us to fix all the problem, to just solve every single problem by just asking the constraint to fall off in this precise way. And also there is a problem with the boost generator that can be solved by just saying that by just setting the leading term in the RA component of the metric to be zero, okay, to start from 1 over R. Okay, so these asymptotic conditions with this twisted parity condition plus this condition, which are always allowed, make these new terms are leading terms. Yeah. No, they're actually leading. They goes in the same way as this guy here. Yeah, there is some R dependencies. We are in Cartesian coordinates. There are dependencies hidden somewhere here. So this is a leading. This is go with the leading term. Yeah? But sorry. Exactly. Yes, like 1 over R. Yeah? But what is interesting and what is important and how this goes. What is important of having this precise form is that you introduce some derivatives here, and these derivatives allows you to, so when you compute, every computation is on you have to compute some integrals. So you have to integrate by parts, and what you get from this structure here is precisely the constraint, okay? So that's the reason, because you can cure many problems, actually most of them, by imposing some restriction on the fall-off of the constraints, okay? So let's say that we have some problems, we have some derivatives, we integrate by parts, and we form the constraints. Okay? Free particles. That's a good question. I'm not sure. No, I'm not sure. Let me think about it. I'm not sure. Well, it's not pure gauge because it's a similar. That's true. Yes, but this is going to these functions here are going to appear in the charge. Yeah. No, but I know what I mean. So that's the answer. So you can prove that well, there is some interesting structure here, which is highly non-trivial, but you can prove that this is actually invariant. These new asymptotic conditions are invariant under these BMS4 symmetries, and they're hypersurfaced deformations that are parameterized by this C and Ci. Where now the follow of how this behave when you approach infinity, spatial infinity, goes in this way. Where here you have the boost that goes with R, the spatial rotations, YA, which are there. And now we have this couple of functions, C and W, which appear here and there, which are now arbitrary functions of the angles. So this is the new thing. So there is a relaxation under asymptotic conditions such that now you don't have to impose any killing equation on this T and W. So they are completely arbitrary. And this is going to be related at the end of the day to the super translation in the null infinity analysis. Okay, so there are some extra pieces here that I'm not going to comment on that because they are not relevant for this analysis. The relaxation is the parity, twisted parity conditions. So the relaxation is given by these two pieces here. Yeah, those are, yeah, of course. This is not, I'm just making a summary of what have been done. No. This is just the super translation story. I'm sorry. Yeah, so these asymptotic conditions are invariant under VMS, under super translations. Okay, so we can follow the canonical approach. Everything is, so you have a tool, you know how to use it. You can extract the generator precisely from this form, where now you have this boundary term that has to be integrated. So it's a boundary term. We have some variations over there in the structure, so you have to impose the asymptotic condition. You have to use asymptotic condition and try to integrate that. In this particular case, for these asymptotic conditions, you can prove that the generator is finite, integrable, and canonical. Okay? And you compute the Poisson bracket of those generators. What you find is that it's the BMS4 algebra in an unfamiliar parametrization. Okay? And it's given by this full expression here. And what is interesting about this, in the same way as in electromagnetism, I'm not commenting on electromagnetism, but you have to believe on that, that the odd part of W and the even part of T combine in order to give, to make sense to the only one function that parameterizes the super translations at the spatial at null infinity. Okay, so you need both of them in order to make sense to the only one function at null infinity. And in the case of electromagnetism, it's even more dramatic because in that case, well, this is going to be quite similar to what I'm going to do with superrotation somehow. But in the case of electromagnetism, in order to have a well-defined boost, a canonical boost, you have to introduce a new field, and the new field is given precisely the extra symmetry that you need in order to make sense to the null infinity case. Okay, so let's say that in electromagnetism, you only have one function, one arbitrary function, but in order to make sense to the null infinity analysis, you need another one. And the another one is there in order to, the other one is introduced through a boundary field, and the boundary field is there in order to have a canonical generator. So, but well, this is not the case in gravity. Okay, so they have imposed some boundary conditions. They have relaxed somehow the boundary conditions such that now you have an asymptotic symmetry algebra, which is precisely the BMS4 algebra in an unfamiliar parametrization. And arbitrary functions now of the angles. Yes, that's the point. So this is the partial infinite analysis. So you have to go to a different gauge in hyperbolic coordinates, and you have to do this analysis in order to. So what is going to happen at the end of the day? They are going to be related in a very precise way, such that they make sense of the only one function at null infinity. Okay, I see. I think so, yes.
Yes. What's the deal? It's BMS.
Is this VMS?
Because in fact the W should be odd to have
Yeah, that's the point.
so in fact some combination of the two.
Exactly, yes. Sorry? Yeah, yes. That's precisely what is done in the paper by Mark and Cedric. Yes. Okay? Okay, so let's go with these superrotations at spatial infinity. You mean here? B is the boost. Here the boost is here. It's separate, yes. Yeah, you have. Yeah, so let's say that these are the boosts. These are the time translations. No, this is yes, that's true. Yes, but this is this is the asymptotic expansion of the yes. So you have to. Exactly. Yes. But what is the way that this is written? Yeah. Yes. So CA and CA are there in order because you have some freedom here. It's a component. The temporal deformation. Yeah, or temporal. Well, there is no U because we are. Yeah, the temporal component. Yeah. Exactly. Yes. And if you want this, so the zero modes of T are the temporal translations, are the zero modes of W are the three spatial translations. Okay, but now they have infinite modes. They are arbitrary functions of the angles. So we are going to try to. I'm going to try to show you how we canonically realize these superrotations at the spatial infinity. In particular, we are going to focus on these diffeomorphisms on the two spheres, direct product with the super translations. Well, the asymptotic symmetry area is actually bigger because we have some subleading symmetries appearing in the chart. That is going to be clarified at the end of this section. So, in order to have superrotations at spatial infinity, we have to propose, of course, some boundary conditions that are invariant in principle under these symmetries. That's our goal. As I already mentioned at the beginning of my talk, the important thing and one of the key ingredients of this approach, of this idea, is that you have to allow the metric to vary at infinity. Okay, it's exactly the same as in the case of null infinity. And so, in summary, what we have to do is to find some asymptotic conditions that are invariant under these symmetries, where now B and YA are now arbitrary functions on the angles. Okay, they are not. You don't have to impose the Killing equation on them, so they have infinite modes. As I already mentioned, we will have some extra symmetries appearing in the chart, which are subleading here in this vector, and the subleading term here in this vector. Okay. Yeah, I will comment on that later. Okay. So asymptotic conditions. This is our proposal. So first of all, as I already mentioned, there is some relaxation such that we ask the metric. We allow the metric to vary at infinity. That means that this function here is not the metric on the two sphere anymore, but some arbitrary functions on the angles. So this propagates somehow such that now you have to modify the follow-off. So you have to relax. You have to relax the asymptotic conditions for the pi RR and pi AB component with two extra pieces, which are arbitrary functions on the angles. Okay, so these two terms were not there before in the analysis of Mark and Cedric. And the other thing that is different is that now this is an arbitrary functions on the angle. Okay. You can prove. It's not. This one, those two were absent. So before this started from precisely in these two orders. Okay. So you can. Well, the absence shift in our case, that is something important, and I will comment on that probably if you want to need more. But we are considering the same as usual. So the labs, the case as 1 plus order r to the minus 1, and the shift, if I remember well, this goes like order r to the minus 2 probably. Okay, this is the usual election of labs and shift. Yes, of course. No, yes, no, okay. No. In this case, for our, no. Of course, okay. I'm not saying of course, but what? Yes, so what is true is that the leading term, so.
Dynamical field are G and pi.
You can, yes, but in this case, it's a choice. In this case, it's a choice, I think. And this is related to the fact that we, yes, so this is related to the ADM energy at the end of the day. Okay? The fact that we have a 1 here is because of that. No, they cannot. No, they are important. They appear in the definition of the charge. So they. I see. Yeah. Mm. Yes, and I'm not sure about that. No, but I don't think so.
The thing is that it will not be for free. Use to set P bar AB, for instance, to 0
Mm. 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 I see your point, but I'm not sure. It's not. At least this question is not relevant for our. Well, as far as I know. That's the reason. Okay. So, well, as I already mentioned, there is since we have relaxed asymptotic conditions, we find some divergences in the pre-symplectic structure that are actually linear and logarithmic divergences. So in the previous case, in the case of Mark and Cedric, they managed to kill this. Well, they only had this logarithmic divergence, but what they used is to have this. So this relaxation was controlled in a way that you introduce this linearized diffeomorphism. So you integrate by parts, and you get at the end of the day the constraints. Now this was not possible anymore. So what we had to do is to use the renormalisation procedure in order to kill those divergences. For that, you have to add some appropriate boundary terms to the Lagrangian, okay, through this expression here, such that now the symplectic structure is modified in this precise way. Okay? You get this extra piece here. And well, after some computations, what you can prove is that actually the divergences, both of them, the linear and the logarithmic divergence, can be cured by setting this precise form for the R component of VR. Okay, this one. Okay, what is interesting of this procedure is that actually this makes the charge finite. So without this renormalization, the charge has some linear divergence, which was not obvious to be killed by this renormalization procedure, but this was. Well, you mean the fields that are, they are all they are these. Hmm? No, this is so you add an extra piece here, such that the symplectic structure gets this extra stuff here. But this has some structure such that this term here can be cured the divergences, yes, by setting BR. You mean the fields? Yes. Well, there is a lot of stuff here. Yeah, because you have relaxed asymptotic conditions a lot. Say you have symplectic. Yes. You have to take the limit are going to infinity. Mm. Mm. No, that this goes directly to the action. Yeah, yeah. This goes to the action. Yeah. Through the symplectic structure. You pick the boundary term such that you kill the divergence. Yes, but it's not just remove the divergence. There is a procedure, yes. But what we are doing is to remove the divergence. No, 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 no. Yes, well, there is a, you can always say, yeah, we use some parity conditions, yes. We impose some parity conditions just to, in order to simplify a bit the computations. Okay, but that at the end of the day, so what is relevant in this case is, yes, we use some parity conditions, which are the same as the one of Cedric and Mark. Okay, and I will comment on that at the end when I write the generator of the symmetry. Okay. Yes, because for instance, there is some, well, yes, I haven't commented on the parity conditions, but what I can say here is that this guy is parity even, this guy is parity odd. So actually, you actually have here in the symplectic structure, you have a R square divergence that goes like a PAB, GAB dot, and that is zero because of parity, for instance. Okay. Now, the other things that are relevant here, so let's say that this guy has a definite parity, the same having with that guy, but this HAB, GAB, and HRR do not have a definite parity. Well, no, that's not true. This guy has a definite parity as well as this guy. But it's the same as the case of Mark and Cedric. Okay, and this is because we wanted to have the super translations in the same way as them, because you have to select one of the parities for T and W. Okay, and we are also saying something about the V and so this full tower of V and YA. They also have a definite parity. Okay, which is the same as the zero modes. So I think they are both odd under parity. Okay, is it? I'm not sure. I haven't thought about it. Okay, so just to comment this, so the charge is finite, but this is still not integrable. So you can follow, there is a typo here, there should be a delta here, but well, doesn't matter. You can obtain the generator of the symmetry by solving this equation here. So it's just the contraction of the symplectic or the presymplectic structure equal to something. And the something can be obtained by integrating that. So in particular, there is some integrable piece, but the non-integrable pieces are given by this four expression here in color brackets. These first two are quite easy to resolve. Well, the way that we do is just to perform some field-dependent redefinition of the parameters, such that now we set this to t and this to epsilon tilde, such that now we declare that t and epsilon tilde are field independent. Okay, that is usual. That's something that you can always do. You can always do because you have some gauge freedom to do that. No, this is not going to generate any algebraic structure. We will have an algebraic, but this is not because of that. This one is fine. Yeah, actually, this kind of this was not before in the case of Mark and Cedric. This is something that they already had. They have to set this f to. It's a field dependent, but this is not going to spoil anything. No. Yeah, they are now independent. Yes. But now, so let's say that the obstruction now, so we were able to cure that with the usual step. There is nothing new with that. What is new is that now we have this couple of extra non-integrable pieces that goes precisely like the variation of this new structure that we have imposed that was not there before. This is how this goes. What we have to do, or what we propose to do in order to cure that problem, is by introducing a couple of extra fields. Okay? It's a symmetric tensor CAB and a symmetric tensor density FAB, such that now we have to modify the symplectic structure in this precise way. Well, it depends. When you, I don't know. It's a matter of the formalism. So we are approaching spatial infinity, so there is nothing escaping from space. There is no fluxes. So you expect to have something that is integrable. You might have something that is not integrable, but well, you really need to put some effort in order to integrate it. Okay. Of course, yes.
There's something to feed.
No. So we're trying to integrate the charge. That's the point. Yes? So there is a piece that can be integrated by just having a field-dependent redefinition of the parameters, which is allowed by the formalism. Okay? But this still remains. So let's say that you cannot propose some field-dependent redefinition of the parameters so that you can kill those non-integrable pieces. So you have to do something else. Yes, we do field redefinition in order to kill those two. The first two ones, which is okay. The first one was in the mark, yes. Because if you want, so let's say that, so let's assume that we are trying to recover the result of Mark and Cedric. For that, you have to set delta G bar equal to 0 because it's now the metric of the two spheres, so it's 0. And you also have to, so this was 0 and that one was also 0. So let's say that the non-integrable piece in the case of Mark and Cedric was just that, if you want. Because all the rest was 0 because of their boundary condition. So this was there before and it was solved by, but considering some field-dependent the redefinition of the parameter. Now you have more freedom. You have this extra subleading symmetry appearing in the chart that you can use in order to kill that non-divergent piece. Okay? But this tool remains. There is no field-dependent redefinition that makes the job. Okay, so in order to cure that, you have to introduce a couple of boundary fields. Okay, and what's interesting of this structure that well, let me go to the next slide and I will show you what I mean by interesting. So you have to modify the symplectic structure again. So let's say that the charge is not integrable. We want to make it integrable. We introduce a couple of extra fields. You do that by modifying again the symplectic structure with these extra 2 fields here. And we prescribe the transformation law of those fields to transform precisely in this way. So the one that will kill the divergence. So let's say that you have modified the symplectic structure. Now you have to take the contraction of the symplectic structure. This is going to carry some delta P bar AB, and you have to use the transformation law of CAB here, okay? So if we prescribe the transformation law of this new field to transform precisely in this way, so delta CAB transform like that, and delta CAB transform like that, you will cure the divergence, the non-integrable piece. You will integrate the charge by doing that. So you modify the symplectic structure, and you prescribe this CAB and FAB to transform in this precise way. Now there is an extra structure, and I will show in a couple of slides, that you also have this, you also have to supplement the transformation law, but these transformation laws, which are precisely the transformation law of linearized gravity in a curved background. Okay? And I will show you precisely what I mean by that. Okay? So you have modified the symplectic structure. You have to compute the contraction in order to try to extract the charge. With this modification of the symplectic structure, you manage to integrate the charge, at least these 2 non-integrable pieces. But you have to continue the computation. And when you continue the computation, you find that there is an extra contribution, surface contribution to the charge, which is given by this expression here. Okay? It's just BH CF and YHACF. And remarkable, these 2 structures here correspond respectively to the Hamiltonian and momentum constraint for 3-dimensional linearized gravity on a curved background with positive cosmological constant. Okay? I'm going to show you in this next slide what I mean by a linearization under a curved background. And for that, let me just propose the following linearization of the metric, where now this G bar AB and P bar AB are, as I already mentioned, and resembles with our approach. Yes, it is already in the solution space. I'm just trying to, it is in the solution space through this modification of the symplectic structure. It is an addition. You mean if I'm trying to relate this to the existing fields in the theory? Yeah, they are no, they are new boundary fields. They are not related to the fields in the. That could be an option, but it's not what we are doing now. Yes, good. Yes. Could be bad, but we don't know. Okay, running out of time. So what I mean by linearized gravity, okay? So let me propose the following linearization. So here we have introduced this new field, Cij and Pij and Fij. And you also have to make some linearization on the lapse and the shift. And this is what you get from that linearization. So what I'm doing this, or what is the result of, how do I get this precise result that you can see from the previous slides, that this is precisely what we get. So we get a couple of terms that are related to the symplectic structure. So we have a modification on the kinetic terms, plus a couple of lapse and shift times the Hamiltonian constraints. And you can get this result by performing this linearization and keeping everything that is proportional to alpha. Okay, you see that so in the usual linearization, you take gravity and you linearize on a background such that you have a graviton, and this should be related to the graviton and its conjugate momentum. You also have something that should go like C dot, F dot, sorry, F dot Ig, Fig C dot Ij, sorry. But that is actually proportional to alpha squared. So what we have here is precisely everything that is proportional to alpha. What is interesting of this is that these are actually the generators of some gauge symmetry, of the gauge symmetry that you have in the case of a graviton, a Pauli Fierce action. And this is the precise form in this context. So they have this precise form, and they are the generators of this. As I already mentioned, there is some extra structure here. Okay, so in summary, what you are actually doing, if you want, is to introduce an extra boundary field. The boundary field carries some, which is seems like a graviton, or at least to some extent to a graviton. This introduces some extra gauge freedom, that is generated by this HCF and HACF. Okay, they have some arbitrary parameters. Now we have, in order to integrate the charge, we have related these two parameters induced by the parameter that appear in the transformation laws induced by the Hamiltonian and momentum constraint, and we have set them to be precisely the boost and the shift in order to integrate the charge. So we have, let's say that we have some epsilon, and we have related this epsilon to be epsilon b, and let's say that we have some epsilon a, and this is precisely ya. Okay, this is precisely what we are doing if you want to. Sorry, you are talking about this one? Yeah. CAB is the boundary. This is the trace, sorry. This is the trace. There is a missing bar. Yeah, there should be a bar here. I don't know what's happening. Yes, it's just the trace. Okay, well, there is something interesting here is that in our case, this lambda is equal to 1/2, which is, this is related to the fact that the spatial infinity is the Sitter hyperboloid in the Weissschmidt analysis. Okay? So after all this imposing some boundary conditions and introducing this couple of extra boundary fields, we were able to integrate the charge. And this is the final form of the integrated charge. So here we have now some YA and B, which are the superrotations. Superrotations in the sense that they are the diffeomorphism on the two sphere. We also have the supertranslation, which are the T and W. In this case, are the same as are in the case of Mark and Cedric, because, well, you only select one of the parities of them. So let's say that all this bracket, everything here in this bracket has a definite parity. So the only the, I don't remember well, but it should be the odd and the even part of those W and T are improper gauge transformations. And well, what is new here is that we have this couple of subleading symmetries. It's epsilon tilde and epsilon r that goes in this precise way. So, well, again, if we want to recover the case of Mark and Cedric, we just have to, so this term will not be here. This term will not be there. Well, and there is an extra contribution to the integrated chart that is precisely the one that goes with the Hamiltonian and momentum constraint of this boundary graviton. So this is the integrated charge, and this is the final form of the generator. So let me go very quickly to the asymptotic symmetry algebra. You can, well, you have the generator, you have everything to compute the Poisson algebra of those generators. And after some, well, it was a very difficult computation, but we managed to finish it. This is the structure that you have. And now, I will comment on that later, but now we have, well, now B and YA are arbitrary functions on the angles. They are not just killing vectors anymore. You also have these W's and T's, which are the super translations, and these subleading symmetries. I will comment on that in the next slide. But what is also interesting, and this is something that we already found in many cases when you approach null infinity, namely the higher dimensional case, as well as the supergravity case, you have this nice structure. So this is a nonlinear algebra, okay, in the sense that this closes with this extra piece here, okay, which is not a cocycle, but a quadratic term on the charges. So this P is related to the epsilon R symmetry, and this HRR is related to the T charge. I assume that the hypotheses are different. Well, this is no, why are you laughing? It's true. Which is the case in this case. But yeah, I guess the hypotheses are there is more in the hypothesis, I guess. We can discuss about it later if you want.
So maybe this related
Sorry? So this is coming with the mass. Yes, it's the mass. Yes. It's an algebra, yes. It's an algebra, but not because of the nonlinear term. It's because, well, you have to raise and lower the indices here, and this is a function now. It's not a constant. Well, yes, but yes. Well, yeah, that's true. We have found this structure in many cases when you approach null infinity, spatial infinity. Okay, it seems to be we found the same structure when you canonically realize the 5-dimensional BMS5, for instance, and yes, yes.
in fact, any asymptotic symmetry just an accident that in some case it becomes an algebra with function by a cocycle. Here, the rule of the game are a bit different because you are working. But in the standard covariant phase space that I know better, I think is that you have to use a modified bracket to close what you call an algebra. So already it smells like an algebra. When you reduce the constant structure to infinity, is there, because you have the inverse matrix somewhere. Your structure constant. If you look up a bracket, you have something. Vanilla pour son bracket.
Yeah. So let me just finish. I have a couple of extras. So as I already commented, there is some similarities with the other case, but now B and W they contain an infinite tower of superrotation modes. Okay. We also find some extra symmetries, these abelian ideals, are parameterized by epsilon r, which their superrotation acting non-trivially. So that can be seen from here. So there is this act highly non-trivial. Well, this was already commented that there is we have this Lie algebraic structure. Well, again, there is some nonlinear contribution that we think that this is reminiscent of the appearance of field-dependent two cocycles in the charge algebra at non-infinity in the presence of superrotations. Well, this was something very painful to compute, but we managed to prove that the Jacobi identity is satisfied, of course. Well, that's an important checking. And it's interesting that in the computation, you really need this nonlinear contribution in order to close the Jacobi identity. Okay, so everything is very robust, let's say. Some comments. Well, I think I will not have time, but there are some extra symmetries. We have to make sense, but well, there are some interesting results in the non-infinity approach. You have to relax the boundary gauge fixed condition that I think is related to your work. Exactly, yes. That is something that is still missing. Yes, and it's a very, Jimber. Let me just finish because. Okay, just so thank you very much for your attention.